In 4.3, we are going to talk about maxima and minima. So we're going to define what an absolute and local extrema is. We are going to talk about critical points, and we are going to describe how to use those critical points to find the extrema on a closed interval. So first we need a definition. The definition of absolute extrema is if we are looking for an absolute maximum, it has to be larger than every other point in the interval. Absolute minimum at some value c, it has to be smaller than every other f of x on that interval. So that is how we define an absolute. On that interval, it must be the biggest or the smallest of every single other point that's in there. And then we would classify it as an absolute extrema. And that gives us the extreme value theorem. If f is a continuous function on some closed interval, so we know it's a closed because it's got those brackets, then there must be an absolute max and absolute minimum over that interval. So there is an extreme value in that interval if it's a continuous function and we include the endpoints. So here's an example. We have a function, it's continuous, and there is a maximum at an x value of 0 that is local. Here's a local minimum. Here is an absolute maximum because it is higher than every other point in the function. There's no absolute minimum if we assume these are going downward. This is local max, this is local min. So we can label it as such. Absolute max is considered a local max, but it is the absolute. This one is a local or relative minimum. This is a local or a relative maximum. So some definitions. A local max is a turning point that goes from increasing to decreasing. We can also say that for the points relatively close to it, it will be the largest value. A local min, we are going from decreasing to increasing. We can also say that, yes, it's a turning point that goes from decreasing to increasing, but for the points that are relative to that point or close to that point, it is always going to be the lowest value. And this is something really important. The critical points occur where the first derivative equals 0 or is undefined. And then that leads us to Fermat's theorem. Fermat's theorem says that if c is a critical point of a function and it's differentiable, we've seen some points on like an absolute value function that point at the vertex of the v would not be differentiable. So this is only for differentiable points. If it's a critical point, then the first derivative equals 0. So here are some examples of some critical points. Here at C, we have a first derivative equal to 0. The slope of our tangent line is 0. We have a horizontal tangent line. Here we have this cusp, it's called, that first derivative would be undefined, but it is definitely a local maximum. Our absolute value function, perfect example where our derivative is undefined at that point, but it is a local minimum. Here, our first derivative is equal to 0, it's a horizontal tangent, but there is no extrema at that point. It's not guaranteed that there'll be an extrema at that point. Here it is undefined, but there's no extrema. So cube roots have some issues where we do have a first derivative, but there's no extrema. If we did that test they mentioned earlier about it going increasing to decreasing, see how this continues the increasing through that point? This continues to increase through that point. That is one indication that it's nothing special, that it's just, sometimes it's referred to as a point of inflection. We'll get into those things later on. So let's look at some examples. What we're going to do is we're going to find all of the critical points for these functions, and then we'll look at the graph, and we'll look and see how the graph works in relationship to those points. Okay, so let's look at part A. So the first thing you want to do to find the critical points is you want to take the first derivative. So it's all the rules we learned about derivatives. So the 3 would drop down in front, multiply by 1/3, that would be x squared, and then it would be minus 5x plus 4. Now, the critical points occur where it is either first derivative is either undefined or equal to 0. That is a quadratic. It's defined throughout its domain, which is all real numbers. So we don't have to worry about a critical point because it doesn't exist. But we do have to worry about a critical point where x squared minus 5x plus 4 is equal to 0. Now we know how to solve that. Factoring is usually the most efficient way to solve it. So we're going to solve it by factoring. And so we see that there is a critical point at 4 and 1. Now if we look here at 1, at the graph over here on the side, at 1 we have a local maxima, and at 4 we have a local minimum. There are no other points where we have a local minimax. There's no absolute anything for this graph because a cubic is going to go forever in both directions. So that's A. Now let's take a look at B. Now what's important is you remember all of your rules of derivatives. So drop the 3 down in front, power goes down by 1, multiply by the derivative of the inside. Now, when finding the critical points here, now 3 is not going to equal 0, so that doesn't cause any issues. But where does x squared equal 0? X squared minus 1 equals 0. And where does 2x equal 0? Well, this is at plus and minus 1, and this is at 0. So this one has critical points at plus or minus 1 or 0. So what we find here, let's kind of dot out these points. Do you see here how it is decreasing then increasing? At 0, that is a local minimum. But here we have this thing happen where it increases but keeps increasing. Decreases, then keeps decreasing. These 2 points are not going to be a local anything. They're actually going to be what eventually we'll look at the curvature of that. So we'll call that a point of inflection. And then lastly, let's do C here. Now in this particular case, we have to use the quotient rule. We don't really have any other ways to do it. So if we do the quotient rule, it's going to be bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square. Now let's pretty up the top here because it's pretty gross. So that would be 4 plus 4x squared minus 8x squared over 1 plus x squared squared. And so we would get 4 minus 4x squared over 1 plus x squared squared. Now, where are the critical points there? Well, the critical points would occur where 1 plus x squared equals 0. So x squared equals -1. Nope, that's not a problem. So that would be where it might be undefined, where the bottom equals 0. But the top equals 0. If you solve that, you get plus or minus 1. And then let's look at our points. Here's a positive 1. Here's negative 1. This is a local max. This is a local min. You can see we decrease then increase. We increase then decrease. So those are local max and mins at those particular points. So critical points are where the first derivative is either undefined, because it's a fraction, because maybe there's some square roots or something, or if it is equal to 0. Now, the last type of examples we're going to do is finding the absolute extrema for a continuous function on a particular interval. So an absolute maximum of a continuous function over an interval a to b, you'll notice that our endpoints have to be included. The critical points or the endpoints is where the absolute maximum will exist. So the strategy, what are you going to do? Well, find the critical numbers. So that would be where the function is equal to 0 or undefined. But since it's continuous, we don't even really need the undefined portion. We're going to plug in any critical points and the endpoints. Whichever is the largest is our max. Whichever is the smallest is our min. So let's find the absolute max and min of a continuous function over an interval. So these are both continuous functions. There's nothing that's going to mess those up. We have an interval that's closed. Okay, so let's start with A. So what's the strategy? Well, the first thing you're going to do is find the first derivative. You're going to find any critical points. Now, the critical point is where the first derivative is either undefined or equal to 0. So in this case, that would be easy to solve. You just solve for x, and that would be 3/2. Now, you always have to ask yourself, is that in the interval they specified? 3/2, 1.5, is a number between 1 and 3. Okay, so the next thing you do is we are going to calculate the value of the function at our endpoints and at any critical points that are in that interval, so 1, 3, and 1.5. Now you're just going to plug those in to the original function. If you plug in 1, you get 0. If you plug in 3, you get -2. If you plug in 1.5, you get 0.25. And then the last step is to label what you found. The smallest value is your absolute minimum over that particular interval. The largest value is your absolute maximum. And if we look at a graph, that's exactly what should happen. We're only showing that graph between 1 and 3. Our highest value occurred at 1.5. It's the absolute maximum on that interval. And our lowest value occurred at -2. So remember, the absolute maximum has to be either at the ends, so we have to test what the ends are doing, or at any critical point along the interval. Okay, now let's do it again. First step, find your derivative. Okay, so there's our derivative. Now, you have to find out what are the critical points for that derivative. So the critical points are where 2x minus 2 over the cube root of x equals 0. Now, how do we solve that? Well, I would multiply through by the x to the 1/3 to help fix that issue. But we know that definitely x is not allowed to equal 0. So that is a critical point. We couldn't plug in 0 there. That's the only thing that would mess that up. So we have to include 0 as a critical point. Now, it happens to be one of our endpoints anyway, but okay. Now, what else? Well, we need to know where that equals 0. If I multiply through by the cube root, I get x to the 4/3 equals 1, so x is equal to 1. Okay, so what do we got? We have to plug in the endpoints, 0 and 2. We have to plug in any critical points that are in that interval. We do have a critical point at 1. If you plug in 0 to the original function, you get 0. If you plug in 2, you get negative 0.8. If you plug in 1, you get negative 2. This is the local minimum, or I'm sorry, it's absolute net. It is the absolute minimum. It's the smallest. This is the absolute maximum on that interval. Now, if you were looking at a different spot of the function, it might be totally different. And if we look over at the graph, here's our absolute max along that interval. Here is our absolute minimum. I totally said that wrong. That's the absolute minimum. That's the absolute maximum. And then that leads you to your homework. So there you go.